Welcome to the deep dive. We're going deep into quantum teleportation today.
Sounds exciting.
Yeah, it is. Now, when people hear quantum teleportation, I think they probably think,
Star Trek?
exactly, like beaming people up or whatever.
Right.
But it's not really like that, is it?
No, it's not about teleporting physical matter. It's more about information. It's kind of like sending a blueprint that lets you reconstruct the original somewhere else.
Okay, so teleporting information, but what kind of information? Why is this such a big deal?
It's all about the qubit. The qubit is the most basic unit of quantum information, and they're the building blocks of quantum computers, which, as you know, could totally revolutionize so many fields: medicine, materials science, even cryptography.
Yeah, so much potential. So to understand quantum teleportation, we got to start with qubits. What exactly are they? How are they different from the bits in our everyday computers?
So imagine a regular bit like a light switch. On or off, right? Represented 1 or 0.
Okay, makes sense.
A qubit is more like a dimmer switch. It can be on, off, or anywhere in between. It can even be in a state called superposition. That's where things get really weird.
Superposition?
It can be both on and off at the same time.
Whoa, okay.
Yeah, kind of mess with your head a bit.
So that's possible, both on and off at the same time.
That's the beauty of quantum mechanics. It's this both at once ability that makes qubits so powerful.
Okay, so we've got these qubits that are kind of breaking the rules of our everyday logic.
Right.
How do we actually teleport them? What's the secret sauce?
The secret ingredient is entanglement. It's this crazy phenomenon. Einstein actually called it spooky action at a distance.
Entanglement. I've heard that term, but always kind of sounded like magic to me.
Imagine you and I each have one glove from a pair.
Okay.
We put them in separate boxes and send them to opposite sides of the world. If you open your box and find a right-handed glove...
I instantly know you have the left.
Right. No matter how far apart those gloves are.
Okay, that's a good analogy, but how is that possible? Are these particles talking to each other faster than the speed of light?
That's a question that puzzled Einstein, too. The connection is instant, but no information is being sent faster than light.
Got it.
They don't send signals back and forth. It's more like they have this shared identity that goes beyond space.
Whoa! Okay, so we've got these entangled particles. How do we actually use them to teleport a qubit?
Let's say you want to teleport a qubit to me. We each have one particle from an entangled pair.
Okay, so we've got two sets of particles. The one that's going to be teleported
Right.
and one that's already entangled. What happens next?
You take the qubit you want to teleport and make it interact with your half of the entangled pair.
Okay.
This basically encodes the information from your qubit onto the whole entangled system.
Oh, I see. It's like merging the information from the original qubit into this, entangled network. But if you can't copy quantum information, how do we know the teleported qubit is going to be exactly like the original?
You're asking the right questions. And this is where it gets really interesting. Combining your qubit with the entangled particle actually destroys the original information.
Ah, so no cloning allowed.
No cloning allowed.
So the original qubit is gone.
Gone.
What about my entangled particle, the one that's miles away from yours?
Here's where the magic really happens. By doing a special type of measurement on both entangled particles, we transfer the information about your qubit to my entangled particle, even though those two never interacted directly.
So the qubit itself isn't actually traveling through space. It's more like its information is imprinted onto my particle through this spooky entanglement connection.
Exactly. It's as if we sent a blueprint through that entangled connection, and now I can rebuild the original qubit state on my end.
Okay, that's starting to make sense. But wait, if this information is being sent instantly through entanglement, do we even need a regular communication channel at all?
Great question. Actually, we do still need a classical channel to send some extra info.
Oh, really?
Yeah. When you do that special measurement,
Yeah?
you get one of 4 possible outcomes. You got to tell me which outcome you got, so I can tweak my particle and recreate the qubit exactly as it was.
So it's kind of like you send me a text saying, hey, I got outcome number 2. Make sure you adjust your particle accordingly.
Exactly. That's a great way to put it.
Yeah, great.
And this classical communication keeps us from breaking the speed of light limit, which is important.
Yeah, got to follow those cosmic rules. So it sounds like we need both a quantum channel through entanglement and a regular channel for these instructions.
Right.
It's like sending a recipe for a cake along with a box of pre-measured ingredients. I still need to follow the instructions to actually bake the cake.
That's a very insightful analogy. It's this interplay between the quantum world and the classical world
Right.
that makes quantum teleportation so fascinating.
It all sounds super complex, but I know researchers have actually managed to teleport quantum information in experiments.
Right. Yeah, absolutely. Back in 1997, they did the first successful experiment. Two different groups, one led by Sandu Popescu and the other by Anton Zeilinger.
Okay.
They both managed to teleport a single photon. A photon is a particle of light.
So it all started with light. What made teleporting photons so hard?
Well, in these early experiments, they used a method called parametric down conversion to make pairs of entangled photons. But sometimes the photons arrived at the detectors at slightly different times.
Oh.
So it's hard to tell if they were truly entangled or just random photons.
So they needed to make sure they were looking at the right photons, the ones that were actually connected.
Exactly. They had to get creative. For example, they used a pulse laser to create photons and then pass them through really narrow bandwidth filters. This guaranteed the photons have very specific properties and a longer lifespan as a wave. That's how they could tell the entangled pairs from the random ones.
So they made those photons more identifiable, even though they were entangled. What about Zeilinger's group? What did they do?
They used something called two-photon interferometry to check the entanglement and make sure the quantum information was actually moving from one photon to the other.
I'm sensing a theme here, a lot of ingenuity just to make these early experiments work.
Yeah, absolutely. And, these early successes opened the door for bigger and more ambitious experiments.
Like teleporting over longer distances?
Yeah. For example, in 2004, they teleported a photon across the Danube River in Vienna.
Across a river? That sounds like something out of a spy movie. How did they send a single photon that far?
They had to use fiber optic cable, but instead of running it across the river, they installed it in a sewer system under the Danube.
Sewer system? That's not exactly the most glamorous place for cutting-edge science.
It's all about practicality, right?
Right. But why a sewer?
The sewer was stable. It protected the cable from temperature changes and stuff like that.
Okay, that makes sense. But even with the cable, they still had to figure out how to send instructions from the sender to the receiver quickly enough.
Yeah.
Didn't we already talk about that, using a classical channel for instructions?
We did, but in this case, the instructions had to be sent almost instantly. Sending them through the same fiber optic cable would have been too slow. The quantum state would have decohered.
Decohered? What does that mean?
It means it would have lost its quantumness. It's like trying to send a message written on a disappearing piece of paper. It has to get there before the message fades away.
Oh, I see. So they needed a faster way to communicate, separate from the fiber optic cable.
That's right. So they set up a microwave channel, like a super sophisticated version of the ones in our kitchens.
Using microwaves for quantum teleportation. Science is so wild. But did this experiment have any broader implications?
Absolutely. It showed that quantum teleportation can work in messy, real-world environments. This means we could build secure quantum communication networks using infrastructure we already have.
Okay, so no more sewer systems, hopefully.
Let's hope not. But that Danube experiment really proved that quantum teleportation could move beyond the lab and into the real world, and it opened up so many exciting possibilities. And speaking of the real world, things got even more impressive when scientists started teleporting quantum information over much longer distances. There was this incredible experiment where they teleported a photon over 143 kilometers between two of the Canary Islands.
143 kilometers? That's like teleporting something from New York to Philly. What are the implications of separating the quantum information from the actual physical particle like that?
That experiment was a huge step towards building long-distance open-air quantum communication. Imagine secure networks that are impossible to hack. Or distributed quantum computing, where quantum computers are linked together over huge distances to solve really complex problems.
It's like building a quantum internet.
Yeah. That experiment showed that we can handle environmental challenges and achieve teleportation over significant distances. And that opens up some really amazing possibilities.
Okay, teleporting photons 143 kilometers through the air, that's insane. How did they even pull that off? Teleportation through the air seems like it'd be really sensitive to interference.
Oh, it absolutely is. They had to overcome some huge challenges. Things like signal loss because of atmospheric disturbances, keeping the clocks at the sending and receiving stations perfectly synced, and developing super sensitive detectors that could pick up a single photon.
Sounds like they had to invent a lot of new technology just for that experiment.
They did use a powerful laser, but the key to their success was a clever mix of techniques. For example, they used entangled photon pairs with very specific properties. They created pairs where the photons' polarizations were linked, but their frequencies could be different.
So remind me, what's polarization again?
It's like, think of a light wave as a vibration moving through space. Polarization is the direction that vibration is happening in. It can be up and down, side to side, or anything in between. So in this experiment, if one photon was vibrating horizontally, the other would be vibrating vertically. But they could arrive at different frequencies, which helped them to filter out all the noise.
Ah, so by using those special entangled photons, they could block out the interference from other light sources.
Exactly, like tuning your radio to the right station. But they also had to create detectors that were so sensitive that they could pick up just a single photon, even with all that atmospheric noise.
Wow, it's like trying to hear a pin drop in the middle of a rock concert.
And on top of that, they had to make sure the clocks at the two stations were perfectly synchronized. They had to be able to pinpoint the arrival time of each photon with incredible precision. Otherwise, they might look at the wrong photon and think it was part of the entangled pair.
Wow, and all of that with single photons traveling over such huge distances. That's a lot of moving parts.
It is. They used a technique called entanglement-assisted clock synchronization. So they actually used entanglement itself to help them sync those clocks between the two islands.
Using entanglement to solve a problem created by entanglement? That sounds almost like a paradox.
Well, that's quantum mechanics for you. It's full of paradoxes and things that just don't make sense in our everyday world. But it works.
Okay, so we've teleported a photon over 143 kilometers. That's pretty mind-blowing. But can we teleport things other than photons?
Absolutely. Researchers have teleported the quantum states of atoms.
Really?
Electrons, even superconducting circuits.
Wow, so it's not just light anymore. This teleportation tech is getting pretty versatile. Can we teleport, like, an atom's quantum state? How does that work?
It's similar to teleporting a photon, but instead of entangled photons, we use entangled ions. Ions are basically atoms that have had an electron added or taken away. This gives them an electrical charge.
So they're using charged atoms.
Exactly. They trap these ions with electromagnetic fields, and then they use lasers to manipulate them and create the entanglement needed for teleportation.
I bet that's really precise work.
It is. Ions are a lot more sensitive than photons. Once you have the entangled ions, you take the atom whose state you want to teleport, and you interact it with one of the entangled ions. Just like with photons, this destroys the original atom state and encodes its information onto the entangled system.
Okay, no atomic clones here either.
No,
so then what happens?
The receiver has the other entangled ion, and they do a special measurement on it to get the teleported information. Then they can use that information to rebuild an atom with the same quantum state as the original.
So it's like we're sending a blueprint through a regular channel, and those entangled ions are like the building materials for putting the atom back together with the right quantum state.
That's a great way to put it. And being able to teleport atoms opens up so many possibilities. Imagine teleporting the state of an atom right into a quantum computer. That could let us do calculations that are just impossible with regular computers.
We're not just sending information anymore. We're sending the actual building blocks of matter into quantum computers.
It's incredible, isn't it?
It is. The possibilities are mind-blowing.
The quantum teleportation is still pretty young, but it's come such a long way. Who knows what amazing applications we'll discover in the years to come.
Okay, so we've talked about photons, atoms. Can we teleport a cat?
Ah, the question everyone always asks. Unfortunately, teleporting something big like a cat is still science fiction. The challenges are just enormous. We'd need an entangled system as complex as the cat itself, with billions upon billions of particles.
And even if you could do that, wouldn't entangling something as complex as a cat destroy it in the process?
That's a question that gets at the heart of consciousness and how it connects with quantum mechanics. It's something we're still trying to understand. It's a real mystery.
Sounds like we're a long way from teleporting cats, or people for that matter. But the fact that we can teleport the quantum states of single atoms is still pretty amazing. And who knows what the future holds, right?
That's the beauty of science, always pushing the boundaries.
Speaking of pushing boundaries, I know there was an experiment where they actually teleported quantum information to a satellite. Tell me more about that.
Yes. They teleported a qubit to a satellite called Milestones, which was orbiting hundreds of kilometers above Earth.
Hundreds of kilometers? What was so special about this Milestones satellite?
Milestones was designed specifically for quantum experiments. It had sensitive detectors and special optics that could receive and send single photons very precisely.
Okay. Why go to all that trouble to send a qubit to a satellite? What's the advantage of doing that?
It's all about building a global quantum network. We can use satellites as relays, beaming quantum information over huge distances. We could connect computers and devices all over the planet.
It's like a quantum internet in space.
That's the idea. Think about it. A world with unhackable communication and a distributed network of quantum computers working together.
Yeah.
Sounds like science fiction, but we're actually getting closer to making it a reality.
Wow, that's a really exciting vision. But back to this experiment. What were some of the challenges of sending a qubit to a satellite that's hundreds of kilometers away?
Well, first of all, sending a single photon that far and making sure it hits its target is incredibly hard.
Yeah.
Especially since the satellite is moving all the time.
Right.
You have atmospheric turbulence scattering the photons. And the constant motion of the satellite makes it incredibly hard to keep a steady connection. It's like trying to hit a moving target the size of a pinhead with a laser pointer from across a city.
That's a great analogy.
They used adaptive optics to deal with that atmospheric turbulence, constantly adjusting the shape of the laser beam to compensate. They also created really sophisticated tracking systems to lock onto the moving satellite.
Wow. Sounds incredibly complex.
It was. Did they actually manage to teleport the qubit to the satellite?
Yeah.
Did they?
Yes, they actually did. And they achieved a fidelity of over 80%.
80%. What does that mean exactly?
Fidelity is like a measure of how accurate the transfer was. A fidelity of 100% would mean a perfect match. They actually beat the classical limit of 66.7%, which is the best you could ever do if you were just using regular methods to send information.
So they proved that quantum teleportation is not just possible, but it can actually be more accurate than regular methods.
Exactly. It's like having a communication channel that's both faster and more accurate than anything allowed by classical physics.
So we've gone from teleporting a single photon across a table to teleporting qubits to a satellite. What's next? What are the next big challenges for quantum teleportation?
Well, one of the frontiers is teleporting increasingly complex quantum states.
Okay.
We've gone from photons to atoms, but what about molecules, even larger systems? The difficulty grows exponentially as the system gets more complex, but the potential payoffs are enormous.
It's like going from teleporting a single brick to teleporting an entire skyscraper. Exactly. Another challenge is teleporting over even longer distances. We've gone from meters to kilometers, but what about teleporting across continents or even to other planets?
Interplanetary quantum teleportation.
For that, we'll need to develop new technologies for sending quantum information through fibers, the atmosphere, even the vast emptiness of space.
That's a really cool idea. But before we get too far ahead of ourselves, what about applications that are closer to reality? What's being developed right now?
One really important area is in secure communication networks.
Oh, yeah. Unhackable messages. How does quantum teleportation make things more secure?
It lets us send information with absolute security, guaranteed by the laws of physics. If anyone tries to intercept a quantum communication, they will inevitably disturb the quantum state.
Mm-hmm.
And that alerts the sender and receiver that something's up.
So it's like having a built-in alarm system that goes off if anyone tries to peek at the message.
It's like having a tamper-proof seal that can't be broken without leaving evidence behind.
I can imagine this being incredibly useful for governments, banks, anyone who needs to keep secrets safe.
Absolutely. Quantum teleportation lets us build these secure communication networks. It means we can extend the range of quantum communication, making connections between distant locations that are impossible to hack. We saw that with the experiment between the Canary Islands.
So it's not just about sending information, it's about building a more secure world, too.
That's right. It's a technology with huge implications for communication, computing, and even how we think about reality itself.
That's a really great point. We've been talking a lot about how quantum teleportation works, but maybe it's time to talk more about why it matters. What are the philosophical implications of all this? If we can teleport information, does that change how we think about reality itself? Or about consciousness?
That's such a fascinating question. Quantum teleportation really challenges our usual ideas about the world. It suggests that information can kind of exist on its own, independently of whatever's carrying it.
Oh, interesting.
It's like separating the software from the hardware.
Right, or the blueprint from the building.
Exactly. It makes you think about the nature of reality in a whole new way. If we can teleport information, does that mean our thoughts, memories, even consciousness, are just information that could be transferred or copied?
Whoa, those are some really big questions. It sounds like quantum teleportation isn't just a technological breakthrough, it's making us rethink the universe and our place in it.
It really is.
But I'm sure we'll have more time to unpack those mysteries in part 2 of our deep dive.
I can't wait. Yeah, there's so much more to explore. And picking up where we left off, it's not just about teleporting information. It's also about being able to manipulate it in more complex ways. And one area that really shows this off is quantum gate teleportation.
Quantum gate teleportation. Okay, I'm intrigued, but maybe we should back up a bit first. What exactly is a quantum gate?
You can think of it as the quantum version of a logic gate in a regular computer. So in classical computers, you have these logic gates like AND or R and NOT gates.
Right.
And they work on bits to do calculations.
Yeah.
Quantum gates are kind of the same idea, but they operate on qubits.
Oh, okay. So they're like the building blocks of quantum circuits, the instructions that tell a quantum computer what to do.
Exactly. They're the basic operations that let us control and process quantum information.
Okay, I think I'm getting it. So if these quantum gates are kind of like the gears and levers of a quantum computer, why would we want to teleport them?
Because building really high-fidelity quantum gates is incredibly hard. They're super sensitive to noise and errors, and those errors can build up and mess up the whole computation.
So it's like trying to build a microscopic clock in the middle of a hurricane.
Perfect analogy.
Any little disturbance could throw everything off.
Exactly. And that's where quantum gate teleportation comes in. Instead of trying to build a perfect gate directly in that noisy environment, we can use teleportation to send a blueprint of the gate from somewhere it's easier to create to the place where we actually need it.
So we're sending instructions for building the gate instead of the actual delicate gate itself.
That's the idea.
That's pretty clever.
It's like sending a master chef's recipe to a kitchen across the country instead of trying to transport the actual dish, which would get ruined on the way. Right. The recipe is much easier to transport, and then you can just recreate the dish perfectly on the other end.
Okay, that makes sense. So how does this quantum gate teleportation actually work? Is it similar to teleporting a qubit's state?
Yeah, the basics are similar, but instead of teleporting a physical gate, we're teleporting the information that tells the gate what to do.
Mm-hmm.
And to do that, we entangle the qubit that's going to be affected by the gate with a special helper qubit.
Helper qubit. So it's like having a qubit middleman.
You got it. This helper qubit is set up in a special way that holds the information about the gate we want to teleport.
Okay.
Then we do a Bell state measurement on the qubit we're going to act on and the helper qubit.
Bell state measurements again. They seem to be everywhere in quantum teleportation.
They really are crucial.
Yeah.
They let us project the entangled qubits onto one of these 4 Bell states, and each of these states has a unique correlation. And that correlation is the key to transferring the info about the gate.
So by measuring those entangled qubits in this Bell basis, we're basically decoding the instructions for the gate. Like those instructions were hidden inside that helper qubit?
Exactly. The result of that measurement tells us exactly what operation needs to be done to the original qubit to implement the teleported gate.
It's like that Bell state measurement is translating the recipe from the quantum language of entanglement into a language that target qubit can understand.
I like that. And this whole process lets us teleport that gate from one spot to another without actually moving the physical gate itself.
Okay, so this quantum gate teleportation, it's not just a theory, right? Have scientists actually done this in a lab?
Oh, absolutely. In 2018, some physicists at Yale managed to do deterministic teleportation of something called CNOT operations.
CNOT operations.
It's a type of quantum gate.
Okay.
And they did this between logically encoded qubits.
Deterministic teleportation, does that mean they got it to work every time?
Exactly. In the early days, quantum teleportation was probabilistic, meaning it might fail. But with deterministic teleportation, you're guaranteed to succeed.
Oh, wow. That's huge for building reliable quantum computers, right?
It really is. It's like knowing the outcome of a coin toss in advance.
Yeah. No more guesswork.
Right. And remember, quantum computers are incredibly sensitive to noise, as we've discussed.
Right.
Even the tiniest things can mess up a calculation.
It's like building a house of cards in a windstorm.
Exactly. So we need fault-tolerant quantum computers, computers that can keep running even when there are errors. And quantum gate teleportation is essential for making that happen.
So it's not just about moving information around. It's about moving it in a way that makes quantum computers more reliable, less likely to break down.
Precisely. It's like building a self-healing system that can correct its own mistakes.
That's pretty amazing. So quantum gate teleportation is kind of like having a quantum mechanic standing by to fix any problems.
You got it.
So it sounds like it's essential for building those powerful and reliable quantum computers of the future.
I think so. And research in this area is moving incredibly fast, with new breakthroughs happening all the time.
It's amazing to think how far we've come since those first experiments teleporting photons. But I understand there's been some fascinating work done on teleporting quantum information over really long distances using fiber optic cables. Can you tell me more about that?
Absolutely. Using fiber optics is really promising for building large quantum networks, especially for stuff here on Earth.
Why are fiber optic cables so good for quantum information? I mean, they're already used a lot for regular internet traffic. But what makes them good for quantum communication, too?
Fiber optic cables are great for a few reasons. First, they create a very stable, controlled environment. The photons are protected from things like temperature changes and vibrations. It's like they're traveling through a tunnel.
Right, so no more bumpy rides through the atmosphere.
Exactly. Inside those cables, the photons travel at the speed of light with almost no signal loss, and that's essential to keep that quantum information intact.
So fiber optics are ideal for sending quantum info across cities, countries, even continents.
You got it. And we've already seen some really impressive experiments teleporting over long distances with fiber optics. One experiment managed to go over 100 kilometers using off-the-shelf fiber optic cables.
Wait, 100 kilometers? That's incredible. And what's even more mind-blowing is that they did this while simultaneously sending regular internet data through the same cables, so they were teleporting quantum information alongside cat videos and emails.
Exactly. That's why this demonstration was so important. It showed that quantum and classical communication can work side by side using the same infrastructure.
That's a game changer. We don't have to build a whole separate internet for quantum information. It's like adding a quantum lane to the information superhighway.
I love that analogy. That experiment was a big step towards making quantum communication a part of our everyday lives.
Okay, so we can teleport through the air, and we can teleport through fiber optic cables. Are there any other ways to send quantum information over really long distances?
There's one more really exciting possibility: satellites. Satellites could create a truly global quantum network, overcoming the limitations of ground-based networks.
So instead of sending information through cables under the ground, we could beam it up to satellites and then back down to different locations. It's like having a network of quantum satellites acting as relay stations, bouncing information all over the planet.
Exactly. It's a very active area of research right now. We've already seen experiments where they teleported qubits to satellites. There are even plans to launch special satellites specifically designed for quantum communication.
Wow, that's amazing. But building a global quantum network sounds incredibly complex. What are some of the hurdles that need to be overcome?
One of the biggest challenges is developing quantum repeaters.
Quantum repeaters, what are those?
They're like the quantum version of signal boosters, like the ones you use to extend your Wi-Fi range.
Oh, right.
Quantum information is very fragile. It tends to decohere, especially over long distances.
Right, it loses its quantumness.
Exactly. Quantum repeaters are like refreshment stations along the way. They periodically refresh the quantum information, preventing it from degrading too much.
So they're like pit stops for the qubits where they can recharge and get a tune-up before continuing on their journey.
That's a great way to think about it. And these repeaters are crucial for building truly global networks that can span entire continents and oceans.
It sounds like building these quantum repeaters is going to be a huge engineering challenge.
It's a massive undertaking for sure. It's a challenge that involves quantum optics, materials science, cryptography, so many different fields. It'll require experts from all over the world working together.
It's really inspiring to see scientists from all these different backgrounds coming together to tackle such a complex problem.
It really is. And the payoff could be huge. A global quantum network would revolutionize communication and computing, and probably a lot of things we haven't even thought of yet. It's definitely a goal worth shooting for.
Okay, so quantum teleportation has this incredible potential to change the world. But as with any powerful technology, there are some ethical questions that come up too, right? What are some things we should be thinking about as this technology keeps advancing?
That's a really important point. Any powerful tool can be used for good or for bad. Quantum teleportation is no exception. One worry is that it could be used for surveillance or to create new weapons.
Yeah, it's that classic double-edged sword. How do we make sure it's used for good and not for harm?
That's a question that needs a lot of thought and discussion. Scientists, policymakers, ethicists, everyone needs to be involved. We need to create international regulations, be transparent about what we're doing, and have open conversations about both the risks and the benefits.
So it's not just about developing the technology itself, it's about developing the ethical framework that goes along with it.
I couldn't agree more. It's not just about what we can do, but what we should do. And those are sometimes even harder questions to answer.
That's a great point. Beyond those ethical questions there, quantum teleportation also raises some really big questions about the nature of information itself. If we can teleport information, does that change how we think about its role in the universe?
Absolutely. Quantum teleportation shows us that information isn't just this abstract concept. It's a fundamental part of reality. We can encode it, manipulate it, and now teleport it. These are things that nobody would have believed just a few decades ago.
So it's like information has its own physical reality. It's not just a reflection of the world, it's actually shaping reality.
That's a really interesting way to think about it. Quantum teleportation is a great example of that. We can separate information from the physical thing carrying it, which suggests that information might be just as important as matter and energy.
Wow. That's mind-blowing. It's like saying that the universe isn't just this big machine, it's also a giant computer, constantly processing and transmitting information.
That's an analogy that more and more physicists and cosmologists are starting to use. And it changes how we see everything, from the nature of reality to the origins of the universe.
Wow, we're getting pretty deep here. So quantum teleportation isn't just changing our technology, it's changing how we understand the universe and our place in it.
It's a revolution in a way.
It really is. Okay, so we've talked about the practical stuff like secure communication and quantum computers. And we've touched on the philosophical side of things, which is pretty amazing. But I heard there's been some really cool research done on teleporting quantum information into systems that already have quantum information in them. Is that even possible?
It is, and it's incredibly exciting because it could lead to some amazing new possibilities for quantum computing and communication.
But how does that even work? Wouldn't that cause problems? If you try to teleport information into a system that already has information, wouldn't that just create chaos?
That's the challenge. It's like trying to merge two really complex computer programs without overwriting or corrupting any of the data.
Yeah, I can see how that would be tricky.
But researchers are figuring out some really ingenious techniques to make it possible.
Okay, I'm really curious now. Can you give me an example?
One approach that's looking really promising is combining entanglement swapping.
Yeah.
Remember that?
Yeah, it's like creating a quantum bridge between two distant locations.
Right. So we can use a similar approach here. We start by entangling the qubit we want to teleport with one part of an entangled pair. Then we send the other part of that pair to the system that already has some quantum information.
Okay, I'm with you so far. So we have our qubit that we want to teleport, and it's entangled with a qubit that's on its way to the target system. What happens next?
We do a Bell state measurement on the qubit we're sending and the qubit that's entangled with it.
Those Bell state measurements are like the secret weapon of quantum teleportation.
They really are. They let us extract the information that's encoded in that entangled state. And the result of the Bell state measurement gives us a set of instructions. These instructions tell us how to change the qubit that's now part of the target system. And that transformation effectively teleports the information from the original qubit into the target system, but without overwriting the information that was already there.
So it's like we're seamlessly weaving that new information into the existing quantum landscape. But how do we avoid breaking the no cloning rule? We can't just make copies of quantum information, right?
That's where quantum error correction comes in. It's a set of techniques that we use to protect quantum information from errors and noise.
Oh, okay.
By combining entanglement swapping with error correction, we can teleport information without accidentally making copies of it.
So it's like having a quantum quality control team, making sure everything is done by the rules.
That's a great way to think about it.
And this ability to teleport information into systems that are already full, that opens up a lot of possibilities.
It really does, both for quantum computing and communication.
Can you give me some examples?
Imagine a quantum computer that's in the middle of a really complex calculation, and you need to add some new information without interrupting the process. You could just teleport that new information directly into the system, like giving it a mid-calculation software update.
Oh, wow. It's like upgrading the computer software without even turning it off.
That's a great analogy.
Yeah.
And that kind of capability could make quantum computers much more powerful and efficient.
What about communication? How would this affect quantum networks?
Imagine a quantum internet where lots of users could send and receive information at the same time without interfering with each other.
Okay.
To do that, you'd need to be able to teleport information to specific spots in the network, even if those spots are already holding other information.
So it's like a quantum internet that's faster, more secure, and can handle tons of information without getting overloaded.
Exactly. And that ability to teleport information to just the right place in the network could really revolutionize the way we communicate in the future.
It sounds like we're headed towards a world where quantum information can just flow between systems without any obstacles, no matter where they are or what's already inside them.
Exactly. And it's this fluidity of quantum information that makes it so powerful, so full of potential. It's like a universal language that any quantum system can understand.
It's amazing to think how far we've come from those early experiments with single photons. Quantum teleportation has become this incredible technology that's changing the way we think about the universe.
It really has.
And it's driving all kinds of new discoveries and innovations.
And we're really just getting started.
Speaking of new discoveries, I understand there's been some really interesting research on teleporting quantum information to systems that are not just far apart in space, but are also very different in their basic structure. Is that even possible?
You're talking about teleporting quantum information to systems that already have quantum information in them, and that information is different from the information being teleported. It's a tough challenge, but it's super exciting because it could lead to even more versatile and powerful quantum networks.
So it's like trying to insert a new piece of code into a program that's already running without causing the whole program to crash.
That's a great analogy. It's like trying to merge two completely different ecosystems without disrupting the delicate balance in either one. But researchers are coming up with some clever ways to do just that.
Okay, I'm hooked. Tell me more.
One approach involves combining entanglement swapping, which we've already talked about, with something called quantum error correction.
Right.
Remember, error correction helps protect quantum information from noise and errors.
Yes.
It's like having a backup system that can fix any glitches that happen during the process.
So it's like we're sending in a team of quantum repair technicians to make sure everything goes smoothly.
Exactly. And by combining these two powerful techniques, researchers can teleport quantum information into systems that already have different quantum information.
Yeah.
Even if those two sets of information are compatible.
So it's like a universal translator for quantum systems, letting them communicate and share information no matter what their internal languages are.
That's a fantastic way to think about it. This ability to carefully teleport information into these complex quantum environments could totally change the way we build and use quantum computers and networks.
It sounds like we're moving towards a future where quantum information can flow freely between all kinds of different systems, creating this vast and interconnected quantum web.
Exactly. And that's what makes quantum information so powerful. It's a tool that could help us make incredible advances in science, medicine, technology. It could usher in a whole new era of innovation and discovery.
It's really inspiring to think about how something that once sounded like pure science fiction is now playing such a big role in shaping the future.
It really shows you the power of the human mind to explore, discover, and create. Quantum teleportation is a journey that's only just beginning, and the future is wide open.
Okay, so we've covered a lot of ground in this deep dive into quantum teleportation. We've gone over the basic ideas, the incredible experiments that have been done, and the mind-blowing possibilities for things like secure communication, super powerful computers, and even a deeper understanding of the universe. But before we jump into the third and final part of our exploration, I want to highlight one more fascinating aspect of quantum teleportation: its ability to unlock new dimensions of quantum information. I've heard whispers about experiments with something called higher dimensional teleportation. Is that something you can tell us more about?
Absolutely.
Mm-hmm.
The research you're talking about involves teleporting quantum information that's not just encoded in a single qubit,
Right.
but in multiple qubits that are entangled in a very special way to create what we call higher dimensional quantum states.
Higher dimensional quantum states. Okay, my brain is already starting to hurt. Can you break that down for me?
Imagine a single qubit as like a point on a line. It represents one dimension of information. But when we entangle multiple qubits, we can create states that are like points on a plane, or even in a three-dimensional space. They represent more dimensions of information.
So it's like going from a one-dimensional line to a two-dimensional plane or a three-dimensional cube. We're basically adding more layers of information to the teleportation process.
Exactly. And teleporting these higher dimensional quantum states opens up a whole new world of possibilities. It's like going from a black and white TV to a full-color, high-definition display. We can send a lot more information, and it's much more complex.
That's pretty cool. But why is teleporting these higher dimensional states so important? What are the advantages?
One big advantage is that it's much more efficient. Let's say you want to teleport a really complex image.
Okay.
If you're limited to single qubits, you have to send the information one bit at a time. That would be super slow.
It'd be like trying to send a huge image file over dial-up internet.
Exactly.
Yeah.
But by teleporting these higher dimensional states, we can send big chunks of information all at once. It's like having a super fast fiber optic connection. The data just flows.
That makes sense. So we're talking about speed. Are there any other benefits to using higher dimensional states for teleportation?
There are. Security is another big one. Remember we talked about how any attempt to eavesdrop on a quantum communication will cause a disturbance?
Right, it's like a built-in alarm system.
Well, with higher dimensional states, that disturbance is even bigger. So it's even harder for someone to steal information without getting caught.
So it's like adding an extra layer of security to the quantum communication.
Exactly. It's like having a safe inside another safe inside another safe.
Fort Knox for quantum information.
Mm.
So higher dimensional teleportation is faster and more secure. Have scientists been able to teleport these higher dimensional states in the lab?
They have. There was one experiment where they successfully teleported a three-dimensional quantum state.
Three-dimensional teleportation.
That's right. It proved that this approach really works, and it opened the door for even more ambitious experiments in the future.
Three-dimensional teleportation. It sounds like something out of Star Trek.
It does, doesn't it? But it's another example of how quantum mechanics is blurring the lines between science fiction and reality.
Yeah, what was once impossible is quickly becoming possible.
Yeah.
So what's next? Where do we go from here with higher dimensional teleportation?
Well, this is really just the beginning. As we learn more about higher dimensional quantum information, I think we're going to discover some incredible new things. New ways to communicate, new ways to compute, maybe even new insights into the fundamental nature of the universe itself. But for now, let's take a break. We'll delve even deeper into these fascinating topics in Part 3 of our quantum teleportation adventure. Welcome back to the Deep Dive. We've been on this amazing journey through the worlds of quantum teleportation, where information can be sent across vast distances in the blink of an eye using the power of entanglement. It's really amazing how this technology could change everything, from communication to computing, even how we understand the universe itself.
Absolutely. We've covered a lot, from teleporting single photons to atoms and even higher dimensional states. But before we wrap up, there's one more mind-boggling concept I have to ask you about. Apparently, you can teleport quantum information using something called the indistinguishability of particles.
You're right. That's a really cool area of research. It lets us teleport information even when we can't directly control or measure the individual qubits involved.
Okay, I'm already lost. How can we teleport information if we don't even know which qubits we're working with? It's like sending a secret message written in invisible ink. We can't see the letters, but somehow the message still gets through.
I like that analogy. And so imagine you have two identical particles that are so close together, their wave functions. Those mathematical descriptions of their quantum states are basically overlapping.
So it's like they're blurry, kind of merged together. We can't tell where one qubit ends and the other begins.
Exactly. That makes it impossible to look at or measure each qubit individually. But here's the cool part. We can still play with their internal properties, things like their spin or their polarization, by doing measurements in different areas where the particles might be found.
So even though we can't tell the particles apart, we can still interact with those individual properties. It's like knowing the flavor of a smoothie, even if we can't pick out all the individual fruits that were blended together.
Perfect analogy. And by carefully manipulating and measuring those internal properties, we can create entanglement between these blurry, indistinguishable qubits. And then we can use that entanglement to teleport quantum information.
So we're basically creating entanglement from this quantum blur and using that as a channel to send information. My brain is starting to melt a little.
It's definitely mind-bending stuff.
Yeah.
But the really cool part is that it actually works. Researchers have done experiments with polarized photons, and they were able to teleport quantum information between two photons that were overlapping and therefore indistinguishable.
So even when the qubits are hidden, we can still use entanglement to teleport information. It's like a secret communication channel that's invisible to the naked eye.
It really is. And this shows us the entanglement is even more amazing than we thought. We're just beginning to understand all the ways we can use it.
It's a great reminder that there's so much we still don't know about the quantum world, and so many incredible discoveries waiting to be made. Speaking of discoveries, earlier we talked about the importance of building quantum computers that are resistant to errors. Can you remind us why that's so important and how teleportation helps us do that?
Quantum computers are incredibly sensitive. Even the tiniest disturbances can introduce errors into a calculation, and those errors can quickly add up and make the results totally meaningless.
So it's like trying to do surgery on a moving crane. Any little bump could be disastrous.
Exactly. That's why we need quantum computers that can handle these errors, computers that can basically self-correct and keep going, even when there's noise all around.
And that's where quantum teleportation can help.
Absolutely. It gives us a way to protect quantum information from those environmental disturbances. One technique that's looking really promising is called error-corrected teleportation. It uses some clever encoding schemes and redundant quantum information to find and fix errors that happen during the teleportation process.
So it's like sending multiple backup copies of the information along with a set of instructions for how to check for errors and fix them.
That's a great way to put it. And this approach means we can teleport quantum information with much higher fidelity and reliability, which is absolutely crucial if we want to build practical, useful quantum computers.
So we're basically using teleportation to quantum-proof our computations, making them more stable and reliable.
Exactly. And that's a big part of why quantum teleportation is generating so much excitement in the field of quantum computing.
It's amazing how something that was once just a theoretical idea is now becoming an essential tool for building the technologies of the future.
It really is. Quantum teleportation is just one example of how exploring the fundamental laws of the universe can lead to incredible breakthroughs. And I think we're just getting started.
Well, I think that about wraps up our incredible deep dive into the world of quantum teleportation. I want to thank our amazing expert for sharing their expertise with us today. It's been an incredible journey.
Thank you for having me. It's always a pleasure to talk about the wonders of quantum mechanics.
And to our listeners, thank you for joining us on this exploration. I hope this has sparked your curiosity and inspired you to learn more about the mind-blowing possibilities of quantum teleportation. Keep questioning, keep exploring, and keep diving deep into the mysteries of the universe.